Okay. Good afternoon, everybody. And my apologies, I was not here in the morning because I was on my way here. So, welcome. I'll add to the welcome of Samriddhi from this morning. Welcome to this meeting around the works of Itamar Procaccia. And before I invite Samriddhi and Rahul for a few things, I'd like to actually give you a very brief overview of the International Center for Theoretical Sciences. I'm a little bit fed up of doing this for the last 8 years now, but most probably this is the last time. So he said, Itamar is here, he hasn't heard you, so we should do it. Okay, good. All right, so it was established in 2007, and the ICTS of the Tata Institute of Fundamental Research from Mumbai is an exciting new adventure in Indian science, and its main aim is to catalyze transformation in the way we do research and education in the basic sciences and mathematics, especially in India. And it combines high quality visitor driven programs of varying durations with top notch in-house research in various areas of the theoretical sciences, with the aim of creating an interactive, participatory environment of research in the basic sciences. The programs have both educational and research components and contain also embedded conferences. So let me just give you a brief on the in-house research. So ICTS is organized as a union of families of researchers, and it's envisaged as a center with a permanent faculty of modest size, not a very huge faculty, but of the highest quality, together with a large floating population consisting of visitors, postdoctoral fellows and graduate students. There is huge support from the associate faculty members from all over India and also abroad, who spend a few weeks at ICTS every year and or interact with in-house research groups on a regular basis. So presently our current research areas include astrophysical relativity, data assimilation, dynamical systems, statistical physics, condensed matter physics, string theory and quantum gravity, physical biology and interdisciplinary mathematics. And we have faculty members in each of these areas, and we grow areas around the people we find. We don't think about an area and then look for somebody, but we get a good guy and grow it, area around it. Okay, and now the programs. So ICTS provides a platform along with resources for researchers to meet during high quality programs of various durations with embedded conferences, as I have said before. And this way it strives to incubate new and emerging areas of research, and cross-disciplinary immersions are encouraged over here. So the programs contribute to transforming the way people do research. They ensure a very participatory involvement of students and postdocs in the process, which is very important in India especially. And they explore new directions in science, foster important research areas, and build a platform for theory to encounter experiment. This is very important because there's our name, fortunately or unfortunately, has the word theoretical sciences, so it's important to put this in front of you. So since 2007, we have organized 95 programs and 26 discussion meetings, which has made a substantial impact on the Indian science scene. And I don't want to give you anything much more in detail except say that we have 3 named lecture series, one in honor of Subramaniam Chandrasekhar, whom I from the university, since I was from the University of Chicago, I had the privilege of knowing him quite well. You two must be knowing him. Srinivasa Ramanujan, of course, and Alan Turing. So these lectures are sort of spread over various areas that I have listed there. And we have very eminent people come and deliver these lectures on important developments in the area of speciality. And the nice thing about our series is that we always organize a discussion meeting in the area of these lectures. So it's just not lectures, but also a discussion meeting where other researchers can speak and also have students come and listen to them. Okay, so this is a slide about today's talk on nonlinear physics of disordered systems, from amorphous solids to complex flows. And we are temporarily located here thanks to we are guests of the Indian Institute of Science, and I hope we have been good guests. And we are very shortly moving to our new campus, and I think some of us want to go and sit there in the next 15 days. It's almost ready. So it's not very far from here. It's this is about half an hour. And here is how it looks. It's more or less done. And this is how it will look in a few years. Okay, so with this I end my presentation. Now I'd like to present a memento to Itamar, so I'd like to invite Professor Rahul Pandit to do the honors. Itamar.
My God, I have to carry it back? Thank you very much. Wow. All kinds of closed boxes, so don't open it now.
And I'd like to invite Samriddhi to formally.
So thanks, Spenta. So it's a great pleasure, as Spenta just said, to have Professor Itamar Procaccia delivering this set of Chandrasekhar lectures. Given the audience here and the other room, the seminar room, which is also filled up to the brink. Professor Procaccia, as all of us know, is a very eminent theoretical physicist and currently holds the Barbara and Morris Levinson Professorial Chair in Chemical Physics at the Weizmann Institute in Rehovot, Israel. Itamar's made significant seminal contributions in very difficult problems in the field of nonlinear sciences, in statistical physics, to name a few. His work on the characterization of strange attractors, on our understanding of multifractality, of turbulent flows, and also on the theory of glasses, and we've had a few talks about these all through the day, have had a lasting impact in these fields. I won't embarrass Itamar by listing all the many awards that he's been decorated with. He's also a member and a fellow of various academies around the world, and as well as significantly for the theme of this discussion meeting, the current chair of the C3 Commission for Statistical Physics of the IUPAP. So with these words, Itamar, it's all yours, and we look forward to 3 fantastic lectures in the coming days. Thank you.
Thank you very much, Sabrina. Thank you, Spenta. Thank you, Rahul. Of course, it's a great honor to be here, not least because I actually knew Professor Chandrasekhar in Chicago. And you must know, Chandra was a local hero in Chicago, even before he got his Nobel Prize. And he was a local hero, not the least because of the awe that he inspired in his postdocs by being in his office every day. You couldn't play hooky if you were his postdoc. And he would come to his office around 6 o'clock in the morning and would stay there until 7 or 8 in the evening, every day, every day. And I got it from Ed Spiegel, who I met when he was already an eminent professor of astrophysics in Columbia University in New York, but he was still awed by these memories, and he told me that when he was a postdoc with Chandra, he made it as a rule to put an alarm clock at 5:30 run to the lab, and when Chandra arrived, say, "Good morning, Professor Chandrasekhar," and run to bed. So that was his way to deal with this issue, because he couldn't face the idea that Chandra will be there and see that he is coming at 11 like a gentleman. Anyway, so actually, Samriti asked me to say a few words about nonlinear physics before we start. And what is special? Why nonlinear physics sort of keeps me off the streets for now almost 40 years? What is so exciting about this? And I think we should agree on a definition of what nonlinear physics is in order to understand why it's an exciting subject. So if you talk to anybody from the Russian tradition, they say that Landau would say, if you have a problem, you have to deal with this in steps. Firstly, dimensional considerations. If you do dimensional considerations and you understand the problem, finished. Well, if it doesn't work, symmetry. And use symmetry and dimensional considerations together, and if it doesn't work, now you need to find a small parameter. And you find a small parameter, you do perturbation theory. Now, nonlinear physics is subjects where all three steps fail. And you have to deal with every problem on its own merit and come up with ideas that are not general, but they are actually good ideas for that problem. And I think what I'm going to discuss with you today is an example of such thing. You have riddles in nonlinear physics. You have to really think, what is the physics and how to deal with this, not with general methods, because general methods usually don't work. You have to do specialized thinking for problems. This is why I find it so exciting and never boring. You know, you never get bored because it's always a challenge. With respect to Professor Chandrasekhar, I would like to also tie my lecture today with cosmology. After all, he was an astronomer, cosmologist, got his Nobel Prize for that subject rather than other wonderful works that he had done in the past. So I'd like to start with the early universe and introduce the query that I want to describe to you today in that context. So you all know that it is presumed that the universe started with the Big Bang, expanding rapidly while cooling. And there was a cascade of gauge phase transitions with the four forces of nature separating out. Today we see inhomogeneous large-scale structures, galaxies that are forming clusters and superclusters. And the clustering is in long chains of filaments separated by large voids. This is important, it's very interesting. Now, we don't really know why, but there is a school that says that these inhomogeneities nucleated during the rapid non-equilibrium quench. That is to say, you had a Big Bang, and then it started to cool down, and upon cooling, you got maybe cosmic strings as possible seeds for galaxy formation. We don't see them today. But we don't see them today because we had metric expansion in that thing, and metric expansion smoothes out singularities. Still, there may be remnants of those. Now you see, cosmic strings, if they appeared, or even deemed, or anything like this upon a quench, is an example of a huge set of problems that I would call topological quantum singularities, which appear in many subjects. And what I would like to discuss with you today is a very limited experiment that has been done in Grenoble that forces us to think about the dynamics, interactions, and the turbulent events that occur when you have quantum topological singularities, and try to understand what can we say about them in a sensible fashion. Just before I go to that thing, let me just point out a new or relatively new paper that saw again that based on a new sample of 355 quasars with significant optical polarization and using complementary statistical methods, we confirm that quasar polarization vectors are not randomly oriented over the sky, with a probability often in excess of 99.9%. The polarization vectors appear coherently oriented or aligned over huge 1 gigaparsec regions of the sky, etc., etc., etc. So there are these large-scale structures that are there that we need to understand. I'll finish coming back to this ground problem, but let me now talk to you about an experiment that had been done in Grenoble in helium-3. Now, helium-3 is a very interesting fluid, and especially when you go to low temperatures, it goes through a series of gauge transformations, and let me tell you what is the experiment. So below the temperature of 10 to minus 3 Kelvin, this helium-3 is a superfluid, and with a simultaneous breaking of orbital spin and gauge symmetries, complex fluid, and the discussed experiment is a temperature of 0.1 Tc, about 100 microkelvin, very, very cold. What do they do in this experiment is pretty unique. They send in neutrons, and the fluid can be locally heated by a fusion reaction of a neutron plus helium-3 that gives you tritium plus proton, and this releases 764 kilo-electron-volt, creating a hotspot of normal fluid within the superfluid, and this hotspot of normal fluid thermalizes within a distance, as I'll show you, within a distance of about 30 micrometers, giving birth to a tangle of quantized vortices. So what actually happens is the following. You have this nuclear reaction, you have a big expansion and warming up, you go above the lambda point for helium-3, and then you go down. Now, when you go down, the wave function forms, but because it's so rapid, the phase of the wave function is different in different regions, and between the different phases, you have quantized vortices that are actually the example here of quantum topological singularities. Now, the analogy to the creation of cosmic strings after the Big Bang, I refer to a very lovely book by Grisha Volovic called The Universe in a Helium Droplets. It's a very interesting book that makes the point that we cannot repeat the experiment of the Big Bang. Nevertheless, helium-3, of course, is not the same. An experiment of this type is not the Big Bang because there's no metric expansion. There is expansion of the gas, there's no metric expansion. So the expansion itself is different. But the quench, after it crossed the critical point, they come back, is not very different. And the gauge phase transformation that are seen are not very different. So there is a point in doing experiment of this type also to learn some things about the dynamics of the early universe. Now, this experiment has been done already a number of years ago and has left on the community a big suspicion. And the suspicion is this. There is a major riddle. The expected lifetime of the vortex tangle, as I'll show you in a moment, is about 10 to minus 4 seconds. Let's say you expect that after 10 to minus 4, max 10 to minus 3 seconds, the whole thing will go back to equilibrium. Experimentally, after a full 1 second, still about 85 kilo-electron-volt did not convert into heat. This energy budget here is measured very accurately with bolometers outside the cell, and you know how much heat has come out, and 85 kilo-electron-volt out of the initial explosion didn't come out. And where is it? Okay, and I will repeat for you this calculation of 10 to minus 4 seconds, and then I'll ask as a riddle, so what is going on? What's the physics? This is an example of those nonlinear problems in which standard methods don't work, and you need to sort of sit back, think about it for about a year, and come up with a proposition. But you know, this is not a standard problem that you know, here's the trick, you just have to sort of work it out. You have to think about what's the physics in a very careful way. So the riddle in this experiment is, where's the energy? Where's the energy that is sort of missing here? Now, in order to put this question on a quantitative level, we have to go through a number of steps. So I'll do step by step carefully. But let me first show you what happens when you have a tangle of vortex lines. So if you create anywhere in a fluid a set of vortex lines, and you now let them go, they begin to interact, and when they interact, they make a what we call a vortex tangle, which is a complete mess. Some people call it superfluid turbulence, But the situation is that every vortex line is interacting with the other. There is the so-called, on the large scales, Biot-Savart interaction, that the velocity that is quantized, or the vorticity that is quantized around every vortex line is affecting the other vortex lines in its vicinity. What happens is they begin to interact, they move, they collide. In the collisions, there are reconnections. The reconnections are a very ill understood phenomenon in this subject, which is crucial to understand well for reasons that I will explain in a moment. And the whole subject of the dynamics of these quantized vortex lines is a far from being settled issue, and I'm going to bring this up as a possibility, especially for the young people, to get into a problem where the riddles are of the order of unity, not of the order of epsilon or epsilon squared. There are many, many interesting riddles. So the creation of a vortex tangle. What I want to do first is sort of guess what is the density of vortex lines that is going to form when you have an experiment of the type that we have in Grenoble. So the point is that I said that if you have a homogeneous quench, the new phase, which is now the superfluid phase, begins to form simultaneously in many independent regions, and in the boundaries of the order parameter, in the boundaries the order parameter may not match. If the Broca's symmetry is U1 gauge symmetry, the domains have different phase of the order parameter, and the defects are quantized vortex lines in a superfluid. By the way, in helium-3, at different temperature, you can have more exotic topological singularities, but like skyrmions, etc. But I don't want to go into those. Let's stay with the difficulty that we have with the quantized vortex lines. Now, the only available theory for guessing what is the density or what is the typical distance between the created vortex lines is the model that was advanced by Kibble and Zurich for the purpose of the Big Bang theory, of the early universe. I'm not going to go through all the complications of this model, but I'm going to use it verbatim as it is. And I'm going to point out that it has one crucial length scale, which I'm going to call L, which is the distance, the typical distance between vortex lines. And what the Kibble-Zurich model says, that the typical distance is determined by two time scales. One time scale is tau sub q, which is the rate of quench. That is to say, this is how fast the temperature is changing at Tc. At Tc is that point where you get when you get the breaking of the U1 symmetry, which in this case is just the phase transition, which is the Bose-Einstein of the Cooper pairing of helium-3. Okay, so this is one parameter, it's the rate of quench. And the other, by the way, we know this F from the model to be of the order of unity. Kibble-Zurich, the latest paper, they offer the number 2.5. The typical length scale, psi 0, that exists in helium-3 is known very well. This is actually the core size of the quantized vortex and is about 800 angstroms, about 0.077 micrometer. And tau t is the thermal relaxation time of the ordered phase. So we actually know these things. They are measured very well. So we know the thermal relaxation time in helium-3, and we know the rate at this, of this phase transition. And what we find when you put all the numbers, that the resulting vortex line density, so L is of the order of L2 minus 2. Don't be amazed that the density has the length scale of L2 minus 2, not L2 minus 3. That is because it's the density of lines. So it has the dimension of L2 minus 2. We find when you put all the numbers in that the inter-vortex distance is about one order of magnitude larger than the core size. And this gives us a density of vortex lines that is about 1.5 times 10 to the 8 centimeter to the minus 2. So this is the Kibble-Zurich. It gives us a density, but we don't know real numbers. How much? How long are these vortex lines? I mean, we know the vortex line the typical distance between vortex lines, and we know the density, but we don't know how long are all these vortex lines together. For that, we need to do the next calculation. So the evolution of a hotspot, that is easy part. That is easy because we know the temperature equation that you have, temperature diffusion, dt is the thermal diffusivity dt times second order derivative, etc. And we know the thermal diffusivity in this medium, 5 centimeters squared per second. And therefore, we can solve immediately for the temperature. And this is E0 is the energy released by the nuclear reaction. This is, again, the thermal conductivity. This is the solution of this problem. And we can therefore very easily ask, what is the size of the ball where the temperature exceeds lambda point? Okay? And the main conclusion is the maximal radius of the sphere where the temperature exceeds Tc, our max is about 26 micrometers. Okay, so that's the ball where temperature, the whole thing is expanding and cooling down. So you ask how much did it expand before the temperature T can no longer exceed Tc, and that's the answer, about 26 micrometers. Great. So now we have from the Kibble-Zurich the density, and now we have the volume. So together, the length of the vortex lines L is the density times the volume, about 11 centimeters. So the total number, or the total length of the vortex lines in this tangle is about 11 centimeters. We know the energy density. That is a measured quantity for helium-3. And we conclude, therefore, that the energy of the vortex tangle is of the order of 46 kilo electron volt. Wow, 46 kilo electron volt. I told you before that we had a missing 70, 80 kilo electron volts. Now this estimate, as you see, you cannot take for better than a factor of 2, 3. So this is the right order of magnitude, which is, to me, was a great surprise. I think this is one of the first examples that the Kibble-Zurich mechanism that cannot be compared with the early universe because we cannot repeat the experiments, seems to give a fairly relevant number that we can trust, and we can say, okay, the vortex tangle has 40, maybe 80, maybe 90 kilo electron volt. That is the energy of the tangle. But I don't think that we can have a mistake of larger than a factor of 2, 3. So we consider this a great success of the Kibble-Zurich model, and our friends in the subject also say, wow, this is pretty nice. In the sense that you get a correct order of magnitude. Good. So now we know how much energy is contained in this vortex tangle that has been created by the experiment, or roughly, up to a factor of 2 and 3. What do we need to do next? Well, we need to now estimate the dynamics of this L. So what is the decay of a tangle? Well, you see, actually, the physics that one knows about is fairly recent. Okay, good. And is connected to the laboratory of Dan Lathrop in Maryland. Dan Lathrop in Maryland was the first person who succeeded to visualize quantized vortices in any medium, and he did it in helium-4. The way he did this trick is very interesting. He took helium-4 below lambda point and seeded it with hydrogen. Now, hydrogen makes little crystallites, and like bubbles in classical fluid, they are attracted towards the core of the vortex line. So now you see this, here is a vortex line, here is a vortex line. Here's a vortex line. Here's, oops, did you see this? These are collisions between the vortex lines. I'll show you this once more because I think it's a beautiful experiment, rather unique. So here's a vortex line. Here, you just saw an event, another event. Here's another event. Notice also that when the vortex lines are rejected from the event, they go wobble. They have waves on them. These are known as Kelvin waves. because Kelvin has discovered them already in classical vortices, but here they're very interesting. And they're interesting because these collisions and these vortex and these Kelvin waves are the actual mechanism for dissipation in these systems. You see, when you go to very low temperatures, viscosity is 0. Nevertheless, you create a system and it decays. Why? The main physics is that you have these collisions or reconnections between the vortex lines. Upon the reconnection, there is a sound wave that is emitted, goes to the boundaries and lost, and the vortex lines remain with Kelvin waves, and these Kelvin waves now form a very interesting dynamics that we call weak turbulence. That you start with sort of a long wave on the vortex lines. These waves interact. They do what we call cascade of energy. They become steeper, steeper, and steeper. And when the wavelength becomes of the order of the vortex core, they create quantum particles, protons, etc., which go toward the boundaries and disappear. So now somehow we need to take care of all this and develop a theory. What happens? This has to go. Good. So this just as an example from numerics to show you how it works. What am I doing? Okay. As an example of how things work, here's a collision between a vortex ring and a vortex, and you see that this leaves the vortex lines in the excited states. These are these Kelvin waves, just as an example of how this looks. Okay, so now we need to understand the decay of a tangle. We have roughly an idea of what is the energy that it has because of the Kibble-Zurich. Now we need to understand how fast it goes before this tangle is going to decay. And this is the source of 10 to minus 3, 10 to minus 4 seconds that I told you before, but that takes about a year to get. And the reason is that already Joe Vinan, who is an expert in superfluid hydrodynamics, has understood already 20 years ago, the density of vortex lines is an important order parameter in the description of the dynamics of these things. You cannot put it apart. As you know, in superfluids, already in the 60s, there were the two fluid models of Landau and Tissa, which connect the supervelocity and the normal velocity together in a two-fluid model. But that model doesn't take into account at all the existence of vortex lines. Therefore, one needs to begin to ask, how can we improve that model and get a correct description of the dynamics of this media? So Mr. Vinan wrote an equation using the first rule of Landau. Let's use dimensional considerations. So when you use dimensional consideration, I call this the production term and the decay term. Dimensionally, both of them are, of course, the same. They go dimensionally the same, like dl dt. So they have the dimensions of length to the minus 2 over second. The parameters that exist in a superfluid is the difference between normal and super velocity. So I'm going to call it VNS. There is the quantum of circulation for the vortex lines, and there is the density itself, L. So the combination of parameters give you the right dimension is kappa times L squared. This is a numerical coefficient. But you can have any scaling function f of the dimensional, of the dimensionless combination, VNS squared over kappa L squared L. Okay? Now, Mr. Vinan had an idea that the production should be linear in VNS. So he said f of x is going to go like square root x. Okay? By the way, we know the parameters, the circulation, the quantum of circulation is the Planck constant over twice the mass of helium-3, twice because you need bosonization of helium-3, which is a fermion. And alpha is just known as the mutual friction parameter in this game. Now, Wienen has assumed that f of x goes like square root x. Why? Because he thought that the production in a turbulent superfluid of vortex lines should be proportional to the difference between the normal and the super velocity. So f of x is going to be square root x, and therefore he got a formula for p of t that goes like L to the 3/2 times v and s. That's the guess of Joe Wienen. Has been used by now maybe in 1,000 papers, at least. Well, it's wrong. Why is it wrong? Because who says that f of x goes like square root x? You know, if we go in a Landau way of thinking and we assume analyticity of f of x, we'll get that goes like L times Vns squared over kappa. That's one possibility. If we say something else, you know, any other thing, you get another thing. What I'm going to argue to you now, that in fact, the way that it goes is like x to the 3/2, and it goes in this way. So the production term is going to be proportional to Vns cubed. Why? I'll show you in a moment. The same conundrum works about the decay term. It's dimensionally the same, so alpha kappa L squared times another scaling function. What Joe Wienen assumed, that this g of x is a constant, does depend on x, and the decay term goes like L squared. Well, is that true? We have to figure out. Maybe yes, maybe no. This is an example where dimensional considerations don't help, they're not sufficient. Now, people tried, since Joe Wienen made your work, to distinguish between these things by doing experiments and numerical simulations in homogeneous systems. It doesn't work. That is to say, in such situations, the distinction for what can be measured between the various possibilities is too small to make a clear statement. So comparison with homogeneous data fail to distinguish between the various dimensionally equivalent forms. So we propose, therefore, to consider inhomogeneous channel flows. And this is, again, an example of sometimes it takes you a year to do something before you can do the next step in figuring out a problem. So you have to set up channel simulations. And when I say channel simulations, I mean this geometry. So you have walls, and you have a superfluid here with velocity difference between the normal and the super that you impose. Let's say it's going to be a parabolic profile here. And what you do in the numerical simulations, you solve the dynamics of the vortex lines, that you start with a random array, you wait until you get a steady state, of course, with periodic boundary conditions. And now you have dynamics that is set up by the Biot-Savart interaction between these things. And you can ask what happens to the various order parameters that you are interested in. So at this moment, we're going to write the equation slightly differently, not like Joe Wienen. By the way, I have all the respect to Joe Wienen, great scientist. So what I'm saying here is not a disrespect, it's just a next step on what Joe has done for about 20 years. And of course, since we now have an inhomogeneous flow, we have also a divergence of a current, but otherwise we have a production and a decay term. And the current term, I'm going to argue to you, can be easily determined by the same simulations to be of this form. It's proportional to the gradient of Vns squared. But in order to proceed, you need to do microscopic theory. Luckily, microscopic theory has been done before. It has been done by Schwarz. And Schwarz wrote exact relationship in this Biot-Savart dynamics for the stretching of a vortex segment. So if S is the position, if S is a segment of a vortex line that is parameterized by psi, then I'm not going to go into the great details. He wrote the equation that this will satisfy. This is the supervelocity. This is the difference between the normal and the supervelocity. S prime is the derivative, the S Decay. And he wrote down equations for both the flux, for the production term and for the decay term in terms of this microscopic dynamics. Neither Schwarz nor us can do this analytically. We have these microscopic forms, but we don't know how to actually integrate them, how to write the result in terms of the order parameters of the normal velocity, supervelocity, and the density of L. But we now have this numerical simulation. Okay, so we can compute on all the vortex lines that we see these integrals here. We can actually form them. We can go dig psi over all the vortex tangle, compute these things, and get an answer. So we do this, and what we find is what I told you. So here's, for example, for the production. So Joe Weinen guess is the blue. The numerical result is the black line. The second form that you would guess if you assume that the scaling function f is analytic along Landau is the blue. And the third form that I told you is the one that we find is this red one. So obviously the red one fits the data much better than the other things. So in other words, when you do comparison not in a homogeneous situation but in a channel situation, the difference is huge. And therefore you can pick up the correct thing. About the decay, we have an agreement between the decay that Joe Weinen has proposed and the numerical data, and therefore we can now proceed. This is, by the way, for the flux. We also have a very good agreement with the form that we propose. So we have a good equation. So now that we have a good equation, we can proceed, right? I mean, where we were in a situation that we did two things. We did the Kibble-Zurek model to determine what is the density of the vortex lines. Then we looked at the temperature expansion. We found the volume of the hotspot, so we can compute the total length and therefore the energy that we have in this vortex tangle. Now we need to look at the decay. So in this case, the production was already done. Now we need to look at the decay, and we know that the decay has to go like L squared, and there's also some diffusion term. So this is now the equation that we need to take into account. And when we do this, well, again, we know the back of the envelope value of these numbers. So this new prime that is known as the mutual friction is of the order of 0.1 kappa, where kappa is the circulation. L0, we know from the calculation before, is of the order of 0.8 micrometer. That's the typical length. The total volume of our hotspot is about, the radius is about 26 micrometer. The decay due to this term, which is of the order of 1 over nu prime, and the density at 0, which we got from the Kibble-Zurek, and is of the order of L0 squared over nu prime, is much, much faster than the diffusivity that you get from this term, which is of the order of the volume squared over dl, and therefore we know that the tau decay, the decay due to this term, is much faster than this fellow here, and when you put the numbers in, we get 10 to minus 4 seconds. Okay, so a long circle to get to a result that on the face of it is very disappointing. We have an experiment. We know that 1 second after the micro Big Bang, energy is still there. We do a calculation, takes a year to do numerical simulation, to do theory, to do thinking, etc. And when everything is said and done, indeed, you find that everything should end up in about 10 to minus 4 seconds. But still, 1 second later, 85 kilo electron volt, according to the experiment, are still there. So what do we do? Well, again, you go home, you weep, you think. What is the answer? Well, it helps when you're in despair to look up at the sky. And what do you see when you look up at the sky? Well, you see a trajectory of a jet plane. Leaves behind two vortices. And what does vortices do? They reconnect. And when they reconnect, what do they make? Loops. Why am I excited about loops? Because there's a huge difference between vortex lines that are in a tangle and loops. Because vortex line in a tangle, everyone is influenced by the bios of R, influence of the other, and doesn't know where to go. It's confused. A loop has a self-velocity, it can escape. Okay? Loop is self-propagating. Now, do we really have loops in the superfluid? Well, it took us another 6 months to do very careful, very high resolution bios-of-R dynamics on vortex lines in a superfluid. And you see, with the Kelvin waves that I told you before, when they become more and more dense, you have also self-interactions and you create loops. We find them in the numerical simulation. Here's a loop. These are 3 time frames. A loop was formed and it's running away. A loop was formed and it's running away. The vortex line itself continues to be here, but these are running away. So maybe this is the clue. Because what we can say now, maybe that's the answer. Vortex reconnection results in the production of vortex loops. Vortex loops are self-propagating, having their own velocity. So let's now estimate now how much vortex loops are going to form, how fast and how much energy will they take with them. So vortex loops, when they're created, they have to be created on the edge of the vortex tangle, because if they're not created at the edge, they're going to interact again with one of the vortex guys and will make reconnection and will be absorbed or disappear, whatever. So the edge is of the order of the inter-vortex distance, that we know what it is, this L that we computed before from the Kibble-Zurich. And they should evaporate on a time scale is about L squared over kappa. These are the only parameters that I have. Kappa is the quantum circulation, L squared, so this is the only time scale that I can make. Again, dimensional considerations, here it's useful. And this is of the order of decay time of the tangle. That is, when we looked before at what is the decay time of the tangle, you know, it was of the order of the very same thing. L0 squared is 1 over L. So the evaporation time of these vortex loops is on the same order of the decay time of the tangle. Thus, the vortex loop can take with them an energy that is of the order of the energy of the tangle. They evaporate on the same time that this thing exists. So here we go. This is the proposition for a solution of this particular riddle, that we have an evolution of a tangle vortex line with initial radius of 26 micrometers and energy of about 85 kilo electron volts. A tangle disappears due to 2 comparably fast processes: the bulk decay of the tangle that we computed through the corrected Wiener equation and the evaporation of vortex loops, predicting coming back to equilibrium within about 1 millisecond or maybe a tenth of a millisecond. But the vortex loops are still there. The evaporated vortex rings arrive to the boundary where they can stay in the metal stable state for a long time. Why? Because helium-3, you cannot ever clean it from helium-4. And on the boundaries, there's always frozen helium-4 that is very smooth. So a vortex tangle can go there, either get pinned or it can go around for a long time without decay. The hidden energy of the Grenoble experiment is thus ascribed to the initial energy of the vortex tangle that nucleated after the micro Big Bang. So we say most of the energy that is missing is the one that was contained in this vortex tangle and taken away by these loops that can reach the boundary and stay there for a very long time. Can we apply similar reasoning to the early universe? Well, actually, I'm now in a business of trying to create a research line that will deal with all these quantum topological singularities, but I have to say I don't know enough. And maybe people here can help me. What are the generic quantum singularities when you have after the Big Bang? People who do string theory, who do cosmology can help. What are they? I mean, I don't know. Are there vortices? Are there skyrmions? Are there more exotic topological singularities? How do they interact? Do they interact? How do they interact? Can you write closure equations for the density as we do here? You know, the Wiener idea that you can write an equation for the density of vortex lines is not at all trivial. Why only the density? Why not other order parameters? So there are questions that need to be figured out here. You know, it's not enough to know what is the interaction between individual guys. You want to know what are the order parameters in order to write equations that you can solve. What can be simulated? At least for vortex lines, we know how to simulate because we know that at least on the large scales, they interact via B sub R interactions. And how we actually do the reconnection when they collide is not so crucial for the macro dynamics. Any ideas that help are welcome. And any sort of even guesses, I mean, will be very, very nice. We want to do it for any universe. We want to do it for helium-3. Of course, helium-4 we're already running. We have a lot of interesting simulations and experiments also with Dan Lathrop. And I think that I should stop here and thank you very much for your attention. Well, of course, this is discussion.
There are two parameters, mutual friction parameters, alpha and alpha prime in your notations. You always took alpha prime to be 0. I mean, does it change? I mean, when you're worrying about the differences, do you have to worry or not?
The one has to do with production, the other one has to do with the decay. So if you want to write what happens in, say, a superfluid that is being driven either by temperature gradient or by a grid or whatever, both are crucial. Here, the creation was through the quench, not through standard ways, and we had to do the Kibble-Zurich estimate to get the density at time 0. From that point on, it only decays. So only one of the alphas are important. The production one is not so important.
And what were the exact boundary conditions you used?
In the simulations, I'll show you. In the simulations, the exact boundary conditions are as follows. So, you have on the walls, you have stick boundary conditions for the super, slip boundary conditions for the normal, and in the X, you have periodic boundary conditions. Yeah.
Wondering why helium-3 and helium-4 is also the same thing?
No. Actually, helium-3 and helium-4 are in principle very different.
Yeah.
For example, the core size is totally different. In helium-4, the core size of the quantized vortices is about an angstrom. In helium-3, 800 angstroms. Huge difference. And the reason is, of course, helium-4 is boson fluid and helium-3 is fermion fluid, so you need Cooper pairing, and that makes the length scales entirely different. Besides, helium-4, the phase position below lambda point is very simple. It's a U1 symmetry breaking. Helium-3 will go through a series.
Right. So which phase are you actually looking at here?
So actually, I'm doing now just below the lambda point. If you go further down, and this experiment will go further down, new things will happen.
Yeah.
So all these estimates are really back of an envelope estimates for the time you went up above lambda point and you come down, and I don't even know what's going to happen below.
Defects will be different, depending
Different
on the
symmetries, different symmetry breakings, and as long as you're going down with the temperature, you're going to see a series of symmetry breakings and new stuff. Not all of them are still known. I was just sitting in an ERC panel recently with an experimentalist brave enough to go to these temperatures and to try to understand what are the singularities that one sees when you go through the series of phases. It's an open subject. Very interesting.
I think some liquid crystals, they have line defects, and people have done experiments on how
Of course, these are easier to see. You don't need to go to such low temperatures. But they're not quantized.
Yes.
Okay? And here you have topological singularities which are quantized. So it's a different story, and the quantization is crucial.
Just to continue on along the lines of Chandra,
can one do a similar thing for helium-4 solid, where you would form
presumably dislocations, loops, or something like that?
Actually, our simulations are done to simulate helium-4 because we take only simple quantized vortex lines as the topological singularities. So we don't really do simulations for helium-3. I don't even know how to do it, frankly. You know, in the sense that one needs to think again, what are the interactions between what singularities at what temperature. As long as it's simple U1 symmetry breaking quantized vortex lines, we know we know the laws of interaction on the large scales. Biosavar, it's okay. We still don't know very well what happens when you break. By the way, I mean, just a side story, you know, what Dan Lathrop, that we're now collaborating with, has discovered in this experiment is something very interesting. He discovered that there is a universal law for the approach of these vortex lines when they come in. And if you write d as the distance, the smallest distance between these two vortex lines, d of t, this goes like a, no, not like, it goes, it is a times t collision minus t. And there are two riddles. Y square root, meaning that it becomes faster and faster as they come in, and what makes the parameter a. That we solved. That you can actually show that for simple topological singularities like vortex lines, there exists a self-similar solution when they're close enough. They come together always like this and like this, you know, this, how to plot it. This, and they come together in a particular way always, and this determines this square root, and the parameter has to do with angles. So that we understand. But what happens in other cases, when it's not simple, I mean, open world, and one needs to.
Yeah, I mean, there are other topological singularities, like as you mentioned, skyrmions, etc.
Skyrmions, for example.
So, you
how do they interact?
Yeah.
You are the expert.
People have studied those things, but will that make a difference to your result? That's what I'm asking.
I'm sure. Okay. I'm sure that the dynamics will be different. The order parameters, maybe not just simple density. You know, I still don't understand deeply why density of vortex lines as an order parameter works so well. You know, I mean, especially when you have a non-homogeneous flow, like a channel flow, you have other, I mean, you see, when you look at the microscopic terms of Schwarz, you know, these integrations here will depend on the shapes. You know, there is here the first derivative, second derivative of the vortex lines. How does it conjure to be at the end well in agreement with just one vortex, with one order parameter, which is the density of the vortex lines, is a mystery. Okay, so there are many mysterious things here. We're only beginning to scratch how to write microscopic equations for this media that appear to work reasonably well and begin to understand what is happening. But more experiments, more simulations, more theory are necessary. And in my opinion, also collaboration with people like you guys who know very well all the symmetry games and what are the possible singularities and topological quantized things will be very useful. Very, very useful.
I have one more question. Suppose one takes a plane actually through the, vortices and just observes the dynamics in that section. One should be able to write down some effective theory in 2 dimensions.
So are you asking, suppose I did numerical simulations, let me see. So let me understand your question. You're asking if I put a plane here?
Yes, exactly.
Yeah, but then, you see, these vortex lines cannot end in the bulk.
Right.
They can end on a wall, on the boundary. So I guess that they will break and you'll just get 2 channels. So you're not going to simplify. You're going to get 2 channel flows with the, with the vortex line going to one wall and then vortex line going to the other wall. So you're not going to get a two-dimensional flow. I could concoct numerically a two-dimensional flow, but then you don't get vortex lines. You get just vortices,
Yes.
vortex points. They don't reconnect. They collide.
Collide, that's right.
They collide.
So you'll have a two-dimensional gas of what is. I just wondered.
Actually, two-dimensional gas of vortices has been studied much more than this mess.
Of course.
Much more. And there is statistical mechanics going back to Onsager and all kinds of things. So maybe that's an easier soluble problem, but it's not this problem. It's a different problem.
Any more questions?
No questions?
I
They
have
usually are the major question.
Professor Narasimha, you want to make a...
Okay. Ah, two-dimensional, well, yeah.
But even otherwise in channel flows, there are all kinds of little banks occurring, not big
What?
ones. All kinds of little banks occurring all the time, sometimes pretty big ones too. So I was just wondering whether in the dynamics you saw any similarities or not.
Similarities in what sense? Between
See, you
classical and
you take a
between-
flow of the kind that you have here.
I mean, are you asking about similarities between the classical and the quantum mechanicals? Absolutely yes. And let me tell you exactly what they are. And you know the answer, I'm sure. If you look at the large scales, there's no difference. The classical fluid and the quantum mechanical fluid look very different on the large scales because the vortex lines are organized in vortex tubes. Okay, like in the case of a classical fluid, and you know this very well. It was already discovered by our friend Patrick Tabeling that the spectrum of turbulence in superfluid and regular fluid on the large scale is the same, Kolmogorov. When you go to small scales, hell breaks loose, completely different. And the reason for the difference is that the classical fluid, the vorticity dissipates, right? I mean, you have vortex tubes, they go to smaller and smaller scales because of the Kelvin circulation and stretching. So the vorticity stretches. Kelvin circulation, as long as viscous dissipation is not important, means that the vortex tubes have to reduce its width, and then viscosity comes in and gobbles it. Here, nothing is gobbled. This is quantized. It's protected. So a quantized vortex line cannot disappear, and it cannot break. It goes from wall to wall, or it makes rings. So the dynamics, the interactions, spectrum, from the point where you are of the order of the vortex distances is totally different. The cascade is no longer Richardson type, is carried by the Kelvin waves. So the cascade to smaller and smaller scales is no longer classical, totally different, and quantum beasts appear. And we don't know. They are very hard to observe. You know, what I showed you, this film is the best that exists so far. But you only see, you know, I mean, you see the things and you can measure this. But to say much more about what happens on the truly small scales of the core size, nobody knows. What are rotons? How do they form? What are the dynamics? They're there. It's clear because energy is cascaded and disappears. Okay, so there must be quantum things that are formed, go to the boundary, and dissipate. So the similarities on the large scale, when you go to small scale, totally different game, and very important to understand because you cannot do a correct presentation also of the large scales without knowing where the energy is going and how. So my aim at this moment is to rewrite the Landau and Tissa two-fluid model in a way that will respect existence of quantized vortex lines. I think it's possible, at least for a channel flow. I think we're almost there. And you can get a new description. But what will happen, as Spencer says, when the topological singularities are different than vortex lines, it's a totally new subject that I'm very interested in, but difficult and challenging.
Any further questions, comments? Itamar, I have a quick question. These loops that you were talking about, I've looked at Dan Lathrop's experimental data, so in the experiments, I don't recall ever seeing any of these loops. Is it because they're too transient, or do you need the right probes? Either light particles or heavy particles to probe them?
I suppose that they're too small. You see, in our simulations, did I show this?
You showed the transient nature in one of your...
No, I mean here. I want to show you this stuff.
Yeah.
Okay.
That's right.
So, I mean, you see, at least in our numerical simulations, the loops that are formed because of self-interaction of the vortex line due to the Kelvin waves. So you have to resolve the Kelvin waves. He sees them only on the large scales.
Yeah.
And then he doesn't see. You see, you have to have, probably, in my opinion, the hydrogen probe is too rough.
That's why I was being, do you have to change the probe? That was my question.
It's massive.
Really have to get a different...
It's too massive. I think it changes the dynamics when you go on the Kelvin waves cascade. It probably screws up the dynamics. Dan knows this and is now thinking about optical methods that would be non-invasive, non-disturbing in order to see some of the stuff we have. We're now beginning to collaborate seriously. So we think together how to actually do things. It's not easy, but I think it's possible.
Yeah,
but these experiments are very important, and I think he's leading in their world in these experiments, and so one should listen to what he does. Very good laboratory.
Yes, because also with the other groups in Prague, etc., they do show that probes matter.
Absolutely.
In how what structures you see depends a bit on the probes.
Also
whether you're using deuterium, whether you're using hydrogen, whether you're using
but you can count the number of these laboratories on one hand.
Sorry?
You can count the number of laboratories on one hand.
Sure.
This subject was neglected for a long time.
Yeah.
The reason that I am trying to say that it's not just helium, it's a whole zoo of problems in which quantum singularity, including Bose-Einstein condensates, which are so popular. But very little has been done on the dynamics, of these things. So there is a zoo of stuff that can be done here, it needs to be done here. So I expect a renaissance of these things. At the moment, 5 laboratories in all the world, in Grenoble, Helsinki, Dan, Ladik, and Nottingham.
Prague, and Okay, so if there are no further questions or comments, let's thank Itamar for a lovely talk. His next lecture is tomorrow at 4 on more amorphous things. Your next lecture is tomorrow at 4 on more amorphous
Another different subject.
Yeah. Okay, thank you.
More nonlinear physics.
We talked about dark energy.